Let us discuss how to find the area of a plane region using the concept of a limit. So let us consider or suppose f is a function continuous on the closed interval AB, where f of x is greater than or equal to 0 for x in the interval AB. We define region R as the region bounded by the curve y equal to f of x by the vertical lines x equal to a and x equal to b, and by the x-axis. So our problem is how to find the area A of region R. Say this is the curve y equal to f of x. We have the vertical lines x equal to a and x equal to b together with the x-axis. So this is our region R. So we have the interval x equal to a and x equal to b. Alright. So to find the area of region R, we start by subdividing the interval AB into n subintervals. Alright, we shall denote the dividing points as x sub O equal to A, x sub 1, x sub 2, and so on and so forth, x sub I minus 1, x sub I, and so on and so forth, x sub n minus 1, and x sub n equal to b. The next step is to then construct n rectangles. By the way, the common width delta x is equal to b minus a all over n. The entire interval AB is divided into n subintervals, each of with delta x. Alright? Next, we are going to construct n rectangles. We construct n rectangles, each of with delta x. So for the first subinterval x sub O up to x sub 1, we construct a rectangle of width delta x and of height to be determined by the absolute minimum value of f on the interval. Okay? Now, we know that f is continuous on the interval AB. And according to the extreme value theorem, if a function f is continuous on an interval AB, if you have an interval AB, the function f has an absolute maximum value, which is represented by this vertical distance, and let us call it as f of capital M. No? That is the absolute maximum value of f on the interval AB. And similarly, it has an absolute minimum value on that same interval. So in this case, the absolute minimum value will be this much. And we shall denote that absolute minimum value as f sub m, or lowercase m. Since the function that we are considering here is continuous on the interval ab, it follows that f is also continuous at every subinterval. And as such, the function has an absolute minimum and an absolute maximum value on each of these n subintervals. So we continue by constructing n rectangles, right? Each of with delta x. So again, we have a common width for all the n rectangles, which is delta x. And the height of the rectangle is determined by the absolute minimum value on the interval. Of course, another way of doing it is by considering the absolute maximum value on the interval. So let us denote the area of each rectangle by delta A. So let delta A sub I be the area of the ith rectangle. Okay, so the area of a rectangle for delta A sub 1, that is the area of the first rectangle, that will be equal to the width, which is delta x, multiplied by the height, which is f of m sub 1. So again, f of m sub 1 refers to the absolute minimum value of f on the first interval. We can write this as f of m sub 1 times delta x. So delta A2 will be delta x, or f of m sub 2 times delta x, up to delta A sub n, which is f of m sub n delta x. We then form the sum of these n areas. So let me clear this region. Okay, so let us form the sum Sn. We form the sum Sn. So Sn is equal to delta A sub 1 plus delta A sub 2 up to delta A sub n. Using sigma notation, this is equivalent to the summation of delta AI, I from 1 to n, which is equal to the sum of our delta AI is f of m sub I delta x, I from 1 to n. Okay, so clearly S sub n approximates the area A of region R, and Sn is less than the area A of region R because we are using the absolute minimum values, or we call these rectangles as inscribed rectangles. And so the area of these n inscribed rectangles will be less than the area of region R. If we are going to increase the number of subinterval, say n is changed to 2n, we will be getting a sum S2n, which is a better approximation than S sub n. Alright? And S sub 2n will be less than the area A, but greater than S sub n. So S sub 2n will be a better approximation of the area, better than S sub n. If we continue on increasing n, no? As we keep on increasing the number of subintervals, say it tends to infinity, our Sn will get closer and closer to the area of region R. Hence, we say that the limiting value of S sub n, the area or the sum of the areas of the n rectangles as n increases without bound, approaches A as a limit. The greater the number of subintervals there are, the closer the value of S sub n to the area of region R. So if we will take on the limit of S sub n as n increases without bound, the limit will be equal to the area of region R. Hence, we say that the area of region R is equal to the limit, excuse me, the limit of S sub n as n increases without bound, or the limit of the summation of delta ai, I from 1 to n, as n increases without bound, or still in another form, a is the limit of f of mi delta x, the limit of the sum, rather, of f of mi delta x, I from 1 to n, as n increases without bound. So this will be the limit definition of the area of region R. Okay. We can also apply the absolute maximum values. In that case, the rectangles that we will be constructing are circumscribed rectangles. Okay? So for absolute maximum values f of mi's, the area will be equal to the limit of the sum of f of mi delta x, I from 1 to n, as n increases without bound. So here we are using circumscribed rectangles. If we are using the absolute minimum value, then we are using inscribed rectangles. Alright? So let us have an example. Find the area of the region bounded by y equal to x squared, x equal to 0, x equal to 2, and y equal to 0. Now, y equal to 0 is your x-axis. So, let us determine the area of that region. Let us make a sketch of the region. So, first, we have to draw the parabola y equal to x squared. Right? Say that is the parabola y equal to x squared. Then we have the vertical lines, x equal to 0, which is actually the y-axis. So y equal to 0 or the y-axis. No. Yeah, that is the y-axis. Actually, we can disregard this one. No, we can disregard this one. X equal to 0. Y equal to x squared. X equal to 2. So this is x equal to 2. And the x-axis there. You can include x equal to 0, but it has no bearing, no? In the region R. So this is our region R. So what is our interval here? The interval is from 0 to 2. Alright? So our delta x is equal to b minus a all over n, or 2 minus 0 all over n, or just 2 over n. So we divide the interval into n subintervals, each of length or width delta x, and let us draw the ith interval. So we are using the absolute minimum value. Let us use the absolute minimum value. Okay, so there. This is the absolute minimum value, and that is our f of mi. So the interval is from x sub I minus 1 up to x sub I. Our x sub O is 0. Our x sub n is equal to 2. So we're just indicating the ith element. This is the ith element. The ith element or the ith rectangle. The width is f of m sub I, and the interval is from x sub I minus 1 up to x sub I. That is equivalent to delta x. Alright? Now, where does it occur? The minimum value of f on the ith interval occurs at the left end of the interval. It occurs at x sub I minus 1. Okay? The interval is x sub I minus 1 up to x sub I, and the minimum value occurs at the left end. No? Here. The minimum value f of mi occurs at x sub I minus 1. Now we are going to express our m sub I in terms of delta x. Okay? In terms of delta x. And how do you do that? If this is x sub O and the right endpoint is x sub 1, that is equivalent to 1 delta x. Alright? At x sub 2, from x sub O, that will be 2 delta x. So at x sub I minus 1, that will be equivalent to I minus 1 delta x. Alright? So at x sub I minus 1, that is equivalent to I minus 1 delta x from x sub O. So we express mi in terms of delta x as I minus 1 delta x. That is my f. That is my m sub I. Okay, the function f is defined by y equal to x squared, or f of x equal to x squared. So let us find f of mi. F of mi is mi squared. But our mi is I minus 1 delta x, quantity squared. So that is equivalent to I minus 1 squared delta x squared. The entire delta x squared. That is f of mi. So we proceed by writing the formula for the area, which is the limit of the sum of f of mi delta x I from 1 up to n as n increases without bound. So the limit of the sum, our f of mi is I minus 1 quantity squared delta x squared. So I minus 1 squared delta x squared times delta x. I from 1 to n and increasing without bound. So the limit of the sum, what do we do with I minus 1 quantity squared? Well, we expand that into I squared minus 2i plus 1 delta x cubed. This will combine to delta x cubed. But what is our delta x? Our delta x is 2 over n. So 2 over n quantity cubed. I from 1 to n. Okay. Let us now evaluate this sum. Let us evaluate this sum. So, let us clear this. We evaluate the sum of I squared minus 2n plus 1 times 2 over n, excuse me, 2 over n quantity cube or 8 over n cube, I from 1 to n. We can write this as 8 over n cube times the sum of I squared minus 2i, which should be 2i, plus 1, I from 1 up to n. We can bring out 8 over n cube because there is no occurrence of the index I. So it's a constant, 8 over n cube. So we bring it outside. And then we evaluate the summation of this sum. So I squared, we have the formula for I squared, which is n times n plus 1 times 2n plus 1 all over 6. You can recall the sum of I squared is n times n plus 1 times 2n plus 1 over 6. Then minus 2, sum of I is n times n plus 1 over 2 plus the sum of the constant 1 is 1n. Alright? If you can recall, the summation of a constant. The summation of a constant is equal to C times n. I from 1 to n. So that will be 1 times n. Alright. So we have here 8 over n cubed. We multiply together n plus 1 and 2n plus 1. That will give us 2n cubed plus 3n squared plus n over 6. The 2 here will cancel. So negative n squared plus n plus n. Negative n plus n will cancel. Okay. Then we combine 8 over 6. That will be 4/3. Oh, wait, let me write it first as 8 over n cubed. And then let me combine this. 2n cubed plus 3n squared plus n minus 6n squared all over 6. So that becomes, let us now distribute 8 over n cubed. And what do we get? That will be 8 times 2, 16n cubed over 6n cubed. That will be 8 thirds. No, n cubed will cancel. Plus 8 times 3n squared over n cubed 6. That will give us, let me see, 4. N squared over n cubed, or 4 over n. Okay? Plus 8n over n cubed over 6. Oh, by the way, 3n squared and negative 6n squared will combine to negative 3n squared. Okay, 3n squared. So this is supposed to be negative. Okay, negative 3n squared times 8 over n cubed over 6. That will be negative 4 over n. And then plus 8n over 6n cubed. That will be 4 over 3n squared. So that is the sum. That is the sum. We then go back to the area A. Right? So it will be the limit of the sum, which is quantity, 8 thirds minus 4 over n plus 4 over 3n squared as n increases without bound. We then evaluate the limit of each term. The limit of 8 thirds, the limit of a constant, is of course equal to the constant itself, 8 thirds. The limit of 4 over n as n increases without bound. So that means that the denominator is increasing without bound. And if the denominator of a quotient gets larger and larger, then the quotient will approach 0. Same thing for 4 over 3n squared. As n increases without bound, it will also approach 0. Okay, so this too will approach 0. So the final answer then is A equal to 8 thirds. Let us write the unit as square units. So that is the area of region R. And in this case, we use inscribed rectangles. No? We use inscribed rectangles. Or equivalently, we use the absolute minimum value. Let us work on the same problem, but we use the absolute maximum value or circumscribed rectangle and see whether we will be getting the same result of 8 thirds square units. All right. So we use, alternate solution. We use absolute maximum value. Okay, so we have the same region R, same boundaries. So x equal to 2, y equal to x squared, then the x-axis. Let us indicate our I at interval. So at x sub I minus 1 and x sub I, and we construct our rectangle with height equal to the absolute maximum value. So in the I at interval, there is the absolute maximum value. So this is the absolute maximum value. That is your f of mi. So delta x just like before, will be equal to b minus a all over n, or 2 all over n. Your a is 0 and your b is 2. So 2 minus 0 all over n. And your maximum occurs at mi. And mi is actually occurring at the right end, which is x sub I. So we express this, just like what we did earlier, we express this in terms of delta x. So at x sub o to x sub 1, there is 1 delta x. At x sub 2, there is 2 delta x. So at x sub I, there will be I delta x. Alright? So xi is I delta x. Next, our fx is x squared. So f of capital Mi will be equal to xi squared, or Mi squared, capital Mi squared. And our Mi is I delta x quantity squared, or I squared delta x squared. So the area using the absolute maximum value is the limit of the summation of f of capital Mi delta x I from 1 to n as n increases without bound, equal to the limit of the sum of f of Mi, that is our f of Mi, I squared delta x squared. Okay? I squared delta x squared times delta x. I from 1 to n, and increasing without bound. So limit of the sum I squared delta x squared times delta x is delta x cubed. I from 1 to n, and increasing without bound. So let us continue. Limit of our delta x is 2 all over n cubed. That is equivalent to 8 over n cubed times the summation of I squared, I from 1 to n, and increasing without bound. So the limit of 8 over n cubed, and the sum of I squared, I from 1 to n, is n times n plus 1 times 2n plus 1 all over 6. So that will be the limit of 8 over 6 is 4/3 n cubed. Then we multiply these 3. That will be 2n cubed plus 3n squared plus n. Okay, so limit of, we distribute 4/3, 4 over 3n cubed to 2n cubed plus 3n squared plus n. And what do we get? That will be 8n cubed over 3n cubed, or 8/3, plus 4 times 3n squared over 3n cubed, that will be 4 all over n, plus 4 times n over 3n cubed is 4 over 3n squared, as n increases without bound. We evaluate the limit. The limit of the constant 8/3 is 8/3. The limit of 4 over n as n increasing without bound is 0. The limit of 4 over 3n squared as n increases without bound is also 0. So our answer is 8/3 square units, and this agrees with our earlier answer. So the area of the region R is 8/3 square units. Whether we use absolute minimum or absolute maximum values. Okay, as an exercise, you can find the area of the region bounded by, so for the first one, y equal to 4 minus x squared, right? The parabola of moving downward, then the let me change this, let me make it 9 minus x squared, there. Then the boundaries x equal to 0, that is the y-axis, x equal to 2, and the x-axis. Alright, so you can make a sketch of that. There. What else? X equal to 0, which is the y-axis. Then x equal to 2, there. And the x-axis. Now, x equal to 0 is the y-axis. So this is x equal to 0, x equal to 2, and the x-axis. So this is our region R. This is where you are going to construct your rectangles. So whether you are using absolute minimum or absolute maximum values. So that will be your x sub I minus 1 and x sub I. If you are using minimum values, it occurs at xi. No? Between these two, the minimum occurs at xi, the maximum occurs at I minus 1. Okay, so that is for number 1. And then another one, let us say y equal to x squared plus 1, x equal to 1, x equal to 3, and the x-axis. So what will be the graph? Okay, there. The vertical lines are x equal to 1 and x equal to 3. So x equal to 1, x equal to 3. X equal to 1, x equal to 3. And of course, the x-axis. There. So that is my region R. We construct our rectangles. So it depends if you are using absolute minimum or absolute maximum. So it should be at x sub I minus 1 and x sub I. Now, if you are using the absolute minimum value, the absolute minimum value occurs at x sub I minus 1. And we will express mi in terms of delta x from x sub o equal to 1. In our example, our x sub o occurs at 0. No? So if it is at x sub I minus 1, there are I minus 1 delta x. But now, your x sub o is no longer, it does not start any longer at 0. No? And it starts at 1. So if that is your x sub I minus 1, your I minus 1 delta x is from x sub o equal to 1. But you have to refer it from the origin. So you have to add 1. So in this case, your x sub I minus 1 will be 1 plus I minus 1 delta x. And if you are using mi, that will be occurring at x sub I, or equivalently 1 plus I delta x. You can use any of these two. Okay?